Okay. So our speaker is going to be Niko Kochendoerfer, who many of you already know. And she is a postdoctorate at Cornell University, and does a lot of research work with solar arrays and with dairy sheep. And then she also has, with her partner, Lewis Fox, has a large sheep operation as well, a large hair sheep operation. So she'll be talking tonight, continuing our theme on forage analysis and nutrition. But before she talks, I wanted to mention that Niko and I have a project. It's primarily Niko's project through a Smith-Lever and a Hatch grant, with federal funds, where we need to interview 15 sheep and goat dairies, commercial dairies, and we need to be sampling the farms, their milk and their forage 2 to 3 times across the lactation of their sheep or goats. And so if you're possibly interested in being part of that study, we might need almost every sheep, commercial sheep dairy in New York. Please contact us. There'll be a grad student. We'll be doing much of the work with it as well, Claire Bloodwick. And so let Niko and I know after the meeting if you're interested, or drop us a line. So with all that, Niko, I'm going to let you go ahead and do your introduction and get started. Okay, thanks so much.
Thank you, Tatiana. Yeah, and in terms of that study, I just want to add, it's not very involved, right? We will, or Claire will come by your farm and collect these samples, and the survey that belongs with that, I think, takes about maybe 15 minutes to fill out, right? Just so that you're aware that there's not much time commitment from your side at all, and obviously all the data that we will collect, if things get published, it will be anonymized.
And it'll be Claire and I will be doing the collections, depending on which one of us does what region. And if there's another farm near you that's also a commercial goat dairy or sheep dairy, that's a big plus for using you. That being that we need 15 farms, we'll probably be begging a lot of you. All right, thanks. So if you have any interest, that really helps us out.
Okay, all right, so moving on to tonight's topic on nutrition. And when I wrote this presentation, I think essentially realized that what I was doing is really writing a talk about carbohydrates. So yes, nutrition with a focus on the carbohydrate fraction in ruminant feed, or in small ruminant feed. And before I jump into some examples, I would just like to repeat some of the basic concepts that Rich started and summarized and talked about last week, and just go a little bit more into the carbohydrate details of that. And first, I'd like to talk about how we actually go from feed ingredients to components to nutrients, right? And what are the different boxes, the different topics here. So our ingredients are, for example, the soybean meal, the hay, the corn grain. And when we submit these ingredients to a commercial lab, like for example, Dairy One, or if we look up values in the NRC or in any other kind of feed library, then we actually find out about the components, the feed components within these feed ingredients. And the feed components that, again, are measurable in the lab or that published as estimates in feed libraries are our protein, our carbohydrates, our fat, and then also water, minerals, and ash. And maybe some of you noticed that I did not include energy here as an ingredient or as a component, right? So energy, let's quickly talk about that. What is that? Where does that come from? So first off, those are the Atwater physiological fuel values, right? So basically what propels everything, our energy, our little motor or engine. And if we put protein, carbohydrate, and fat in a bomb calorimeter, then we can acquire kilocalorie values per gram of unit protein, carbohydrate, and fat, and they will be 4 kcals per gram of protein, per gram of carbohydrate, it's also 4, and then for fat, so fat is more energy dense in a feed, and that counts for humans as well, has or yields 9 kcals per gram. So that's where that is coming from. Now for ruminant feeds, when we say energy, what we really mean is the carbohydrates, right? The carbohydrate fraction is really our major fuel source. That is really where the energy is coming from. Now, why is that, right? I mean, fat has 9 kcals, it's much more energy dense. But thinking back to our like feed analyses reports from the lab, we have like maybe 3% of the dry matter is fat, right? Or 2.7%, right? So it's tiny compared to our carbohydrate fraction, which is the NDF, right? Our fiber and our non-structural carbohydrates both together. That's our carbohydrate fraction, and that is actually the largest proportion in our feed and is often well above 80, right? And then the protein, I don't know, could be anywhere between maybe 9 and 18 or 20, right? Depending if we're feeding forage or byproduct. So really the energy is coming from the carbohydrate fraction because it's the largest one. Another interesting thing or thing to consider about carbs is that they cannot be stored in the body sufficiently, right? So fat, we all know that can be stored in the body, and so can protein in cells, right? And that needs to get replenished frequently, but it can also be stored. That's not the same for carbohydrates. They need to be made readily available through the feed that we're giving to our animals to be able to then propel metabolic processes, right? Like maintenance, growth, or lactation. So that needs to be part of the feed. And the most efficient precursor for our energy really in the body, or in other words, for our glucose, is propionic acid. And propionic acid, we'll talk a little bit more about that, is a volatile fatty acid, right? That gets generated in the rumen by rumen microbes. And their favorite substrate or their favorite component, right, is non-structural carbohydrates. In other words, starches and sugars. So now when I talk about plant carbohydrates, really what it is all about is cell contents and cell wall materials, right? So this is our fiber, our structural carbohydrate, and then conversely, this is our non-structural or non-fiber carbohydrate right here. And we can see in our fiber, we have our NDF, ADF, so hemicellulose and cellulose, as well as lignin, right? And then also pectic substances, notably, that are fermented, just like fiber, or very similar to fiber. And then here we have our starches and our sugars in the cell content materials, or non-structural carbohydrates. And yeah, the propionic acid, the most efficient precursor for glucose, our energetic substrate in the body that propels our metabolic processes, our production, right? Their favorite feed component is non-structural carbohydrates, right?
So Niko, when you say "our," you're meaning sheep and goats and cows, not necessarily us humans, right?
No, not humans. No, our animals. Like when we.
And then do you want to quickly, I'm sure most people know what NDF and ADF are, but do you just want to say what that acronym stands for?
Sure, Tatiana. NDF is neutral detergent fiber, right? Or the fiber that is soluble in detergent, and ADF is acid detergent fiber that is soluble in acid. Lignin, on the other hand side, is a very complex chemical compound that is also fiber that is not soluble in either detergent or acid, right? And because of that, it is not available to the animal or to the rumen microbes for digestion, right? So lignin is is a very unavailable part for digestion. And we'll get to that in a second. Important to know is also that of the volatile fatty acid production that happens in the rumen, only about 1/3 is propionic acid, right? So propionic acid is actually, it's important. And because of that, we do have a sizable requirement for that in feed. Other words, non-structural carbohydrates, starches, or sugars, okay? And if there's any questions, please, feel free to interrupt at any time or put something in the chat box. I can see the chat up here, so yeah, even if you write it, I should be able to get to that question right away. All right, so yeah, glucose, propionic acid, non-structural, starch, and carbohydrates. Okay, so we went from our feed ingredients to our feed components that are measurable in the lab. And now these feed components, they do not right away become nutrients that are available to the animal for metabolic processes. They go through first a fermentation process, right, in the ruminant, in the rumen, in the cecum, and in the large intestine. And what happens there is that the rumen microbes digest carbohydrate into volatile fatty acids. Because of that, often ruminant nutritionists say that we're not really feeding the sheep or the goat, right? We're actually feeding the rumen microbes because they have to take whatever feed components or feed ingredients we throw at them and turn it into substrate that then can be used by the animal for metabolic processes. And what also happens there is microbial growth, right? Microbial protein gets developed because as we offer carbohydrates, the microbes digest these carbohydrates and they multiply. And as they multiply, they form cells, or they are, consistent of cells. And because of that, microbial protein increases. And then there's also a rest of unfermented feed that remains there. And so once the microbes have digested the carbohydrates into volatile fatty acids, those get taken up, right, by the rumen and by the animal through the rumen walls into the capillaries, into the bloodstream. And that is actually where they then become available to the animals as nutrients, right? And the nutrients are amino acids coming from the protein. They're the volatile fatty acids coming from the carbohydrates. And those are notably acetic, propionic, and butyric acids, whereas the propionic acid is the most efficient precursor to our glucose, or our most efficient energy substrate. All right, and then whatever happened in the rumen here, microbial microbes that are still in there, B vitamins, some of the starches, the lipids, the undigested feed, that moves further down in the digestive tract into the abomasum, into the small intestine, where it then gets further digested or absorbed, right? Again, through the intestinal wall into the capillaries or into the bloodstream, where it also then again becomes available to the sheep or the goat as nutrients, amino acids, or volatile fatty acids. All right, so we actually covered quite a bit of ground here. So we went from our feed ingredients to the components, through the to the fermentation process in the rumen, the digestive process in the abomasum and small intestine. Whatever does not get absorbed through the rumen wall or absorbed into the bloodstream in the small intestine, then remains or gets basically expelled as feces, right? So there's quite a bit of undigested feed, undigested microbial protein. So if the microbial growth in the rumen was actually substantial, then not all of that microbial protein can be taken up in the small intestine, right? And there's going to be microbes left over that will also come out as feces, as undigested protein. And then there is also microbial growth happening in the feces itself, right? So everything, again, that didn't get fermented or digested ends up in the feces. The rest gets absorbed by the animal as nutrients, and then further downstream in the body used for maintenance, for example, right? So dry, early pregnant ewes or rams have a maintenance requirement. So these nutrients have to support or have to be able to support their basal metabolism, right? Breathing, for example, heat exchange, all that, temperature regulation, exercise. So if they have to, let's say, walk to the water quite a bit, or if they run around in circles with their friends because they're happy, then that would also be a maintenance requirement, right? It also gets used for growth. So our weaned lambs and our yearlings, they have quite a bit of bone, muscle growth to do, and then it gets also used for fat, right? And the fat here, the main lipogenic precursor or substrate is the acetic acid, and to some extent the butyric acid, right? And then lactation, early, mid, and late, these nutrients through the bloodstream get absorbed by the mammary gland, drawn into the mammary gland, and there through a variety of biochemical processes remodeled back into components, into protein, lactose, and milk fat, right? So this whole process then for lactation goes backwards, basically. All right. And yeah, so this is the background. This is really what's behind all that. And now I would like to really get into the utilization of carbohydrates, right? And I'm going to do that using an example, and I'm going to compare alfalfa with corn. So alfalfa has a very high proportion of structural carbohydrate, and corn has a high proportion of non-structural carbohydrate. And how do these two actually compare, and what reaches the animal from these two different feedstuffs? So the important factors really are here, the fermentability and the digestibility of the carbohydrate fraction, right? Going back to this, how much of that carbohydrate is actually available to the animal in form of nutrients, right? And how much of the digestive products are available to the animal as nutrients. So that is basically, that's a really important factor in this, how much is available. And yeah, and how much of the microbial production can be taken up in ruminant small intestine. And basically what it comes down to is how available is the fiber and how available is the non-fiber fraction to fermentation. Now, looking at this goes back to the Atwater fuel or energy estimates, right? We have our, here we have our feeds. And again, I'm going to compare alfalfa hay with corn. And that here goes for just the kernel. And we have a gross energy estimate here. So 3.89 versus 4.41, so not quite that different. And then here we can look at our fecal losses of the gross energy. So what does that mean? How much of the energy actually, right, or energy providing substrate in these two feeds gets lost in the feces. And obviously the difference of that is then available to the animal. And we can see here that there is quite a bit of fecal loss for alfalfa, and that there is very, very few fecal losses in percentages for corn. So now, how does that look downstream when we're looking at the energy that is available for lactation? So this is NEL, netto energy available for lactation, right? So this is almost half, right? So for corn, there's almost twice as much available to the animal for lactating, for production of milk, than there is with alfalfa hay. And maybe that's surprising because alfalfa, we all know that, is so high in protein, right? But it's really not just about the protein. And the question here really is, why is that? And the answer to that is, everyone, I mean, knows how alfalfa hay looks like. And we all know that it is very, very stemmy. And the main material in the stem is lignin, right? And here's a lignin molecule, a picture of a lignin molecule. It's very complex, and the microbes in the rumen are not really able to digest it, right? They cannot break it down in the rumen. And because of that, Because the fraction of that indigestible material is so high, we have this large amount of energetic fecal loss here for the alfalfa. The corn, on the other hand side, if we're thinking about the corn kernel, right, does not have that. It has a hull that consists out of fiber, yes, but that's very thin, almost negligible. And inside of the kernel, there's starch and gluten, right, or protein, right? So hardly any lignin. So this is energetically available to the animal almost in its entirety, minus obviously our urine methane losses and our heat losses of that, right? So again, this is the availability of that hinges upon like the composition of the carbohydrate fraction, right? And in this case, the NDF is not available to oh, good question. Is that MKID? You know what? I'm thinking that must be kilogram. Yeah, must be kilogram. Yep, sorry, I should have looked that up. I did not. So the question was, is that mcal per pound or per kilogram? And I'm thinking it's kilogram. I'll confirm that though. Yeah, but anyways, the difference here hinges upon the availability of the fiber, which is not very available here, versus the non-structural carbohydrate right here is very available. Right now, looking at the if I can. Yeah, looking at the protein content on the other hand side, right? Like this is a bad rep for alfalfa. However, alfalfa has a lot of protein, right? So if we have a good quality alfalfa, 16 to 20% protein, that is mainly in the leaves, and it has also a high proportion of bypass protein due to a very fast rate of passage through the rumen. Tatiana will elaborate on that in the next talk, I think, and that means that amino acids get absorbed very efficiently and directly in the small intestine. So this is actually, it's a very valuable feed, however, not for its carbohydrate fraction. And then for corn, right, there is a drawback, there is a trade-off, and that trade-off is that the protein content lays somewhere between 8 and 10%, and with that is very low. Okay, so now moving on to another consideration that is very important when it comes to feeding animals, right? What about dry matter intake? So how is dry matter intake controlled? What does it depend on? And what does the carbohydrate fraction actually, or what can the carbohydrate fraction tell us about our dry matter intakes? And so again, the first question here is the relationship of NDF or fiber carbohydrate fermentability and digestibility and its influence on dry matter intake. And again, how fermentable is the fiber in the diet? If it is really highly fermentable, right, passage rate will be high, meaning that the feed moves through the rumen very quickly, right? So because it gets digested quickly, because the rate of digestion is fast, right? So I have a highly fermentable feed, right? Fiber in the rumen that gets digested very, very fast. And because of that, moves through the rumen very quickly. And that means that the rumen is often empty, or it empties faster, right? So the animal will become hungry quicker and feed intake will be higher. The other consideration is that there is space. Now, if I feed something that is very high in lignin, or in something, or in hemicelluloses that are maybe not as digestible, then rumen fill will be higher constantly, right? There will be more content in the rumen. We see on the left side, really, you know, that little pouch there, the animal will appear full. And because of that, feed intake will be lower because the feed takes longer to move through the rumen. So again, the question when it comes to dry matter intake is really how fermentable is the fiber in the diet. And here, I'd like to just briefly introduce a concept from Mike Toney that he developed together with Dr. Hogue. And that is really the concept of potentially fermentable NDF, or potentially fermentable fiber. And I believe that Tatiana will go into even greater detail on that topic next time, but I'm just gonna here briefly introduce it. So we have our potentially fermentable fiber, and the other important vocabulary here is INDF, or indigestible NDF, so the fraction of the fiber carbohydrate that is not available for digestion. We have our digestible dry matter, right, which is essentially our TDN, our total digestible nutrients. And we have metabolic fecal losses, so MFL. And that is basically the microbial matter in the feces that does not get picked up by NDF feed chem in the feces. So these are losses here at this point. And so that's the vocabulary. And our potentially fermentable fiber can be calculated, right, by using feed library values, for example, of the NRC or other feed library values, and that are mostly being collected at one-time maintenance, right? And we can calculate that potentially fermentable fiber is our total NDF, so our total structural carbohydrate, minus the indigestible NDF, right, which is essentially everything that is indigestible dry matter, so 100 minus the digestible dry matter, and then minus the metabolic fecal losses, right? So this right here is the INDF, so our potentially fermentable fiber, or our fiber that is available for fermentation in the rumen, can be calculated by the total value of NDF minus the indigestible NDF that is part of that fraction. All right. Now, Mike actually collected quite a bit of data on that, and one synthesis of that data is this graph right here, and I'm just gonna walk you through that because it illustrates, I think, very well how dry matter intake and percentage of body weight relates to potentially fermentable fiber, right, and indigestible NDF, both in percentage of the dry matter. So we have three axes here. Again, dry matter intake, INDF, not available to the animal, and then potentially fermentable fiber available to the animal. And we can see by this trajectory right here, right, that the higher the potentially fermentable fiber is in percentage of the dry matter, the higher dry matter intake is in percentage of body weight, right? It goes up here. So when we're here at, let's say 30 right here, okay, we can calculate with about a 4%, or we can look at a 4% of body weight dry matter intake, right? While if we're lower, that goes down significantly, okay? So the takeaway from the slide, very simply, the higher the digestible fraction of the NDF, the higher dry matter intake. And now I'm actually gonna X out of this and show you Mike's feed library here. And I wanna look at two different grass hays together. So first off here, we have our ingredients, right? There's a lot here. We're gonna look at these two highlighted hays, orchard grass, that's early bloom, and then orchard grass hay, late bloom. And up here we have our dry matter, right, 90%, our digestible dry matter, or TDN, same thing, 65 and 54. So there's quite a difference, right? The early bloom is higher in TDN. Crude protein, also early bloom is higher in crude protein. Actually, the late bloom orchard grass hay is quite low. Now, looking at the NDF fraction, so the NDF in these two hays compares at 57 to 67, right? So it's, yeah, but 10% points higher in the late bloom, okay? And just by looking at this, this is lignin, right? There's at least, I would say, 3 percentage points maybe that are lignin that are responsible for that. Metabolic fecal losses lay at 15 percentage points for forages. And then we have our indigestible NDF at 20 and then at 31, right? So not surprisingly, the late bloom orchard grass hay has a much higher proportion of indigestible NDF within the NDF. However, if we look at our potentially fermentable fiber, right, or the fraction of the NDF that is actually available to the animal, they're very, very similar, almost the same. Right? So the takeaway here is very simply that just merely looking at NDF is not gonna is not gonna tell us a lot, right? Because we will have to know not just the amount of the NDF, we will have to know how available is that NDF to the animal. And one way to do that is by determining indigestible NDF and potentially fermentable NDF, right? And here we have our our second carbohydrate fraction, the cell interior content, non-structural carbohydrates. Also much lower in the late bloom hay. That is likely because there's not as much sugar, soluble sugars or sugars in general available when the plant matures more. Okay, now I'm gonna get back to this. All right, so now we talked about dry matter intake, and we talked about availability of different carbohydrate fractions, right? And now I would just like to do an example of ad lib or free choice feeding of a fully pelleted ration, a complete pelleted ration that we did at Cornell in a 2-year feeding trial in a dairy setting. And I'm going to do that just to show you what kind of impact actually different proportions of the carbohydrate fraction have on animal productivity, right? Like what's the impact of starches and sugars versus fermentable fiber or fiber carbohydrate. And so again, this was in our little sheep dairy here, and we fed a fully pelleted ration that looked very similar to this. That was soy hull based and cornmeal based, and yeah, formulated to be completely balanced. And here's an interesting fact: soy hulls are up to 65% fermentable, or have up to 65% PF-NDF in their feed analysis, or in their feed component analysis. So that's really, really high. We did a 2-year 9 lactation feeding and milking trial, and the 3 experimental diets that we fed, they contained low, medium, and high percentages of soy hulls in the dry matter, and because of that had low, medium, and high potentially fermentable fiber. And yeah, I said that included here to illustrate the impact of the 2 carbohydrate fractions on milk yield and on feed efficiency. So the way we formulated those diets was we used FeedForm, which is Mike's feed formulation program. And here you can see that there was a estimated dry matter intake that was very, very high, right? And actually not very crucial for that particular ration, because it was offered free choice or ad lib, meaning that they could eat as much of these pellets as they would want to. And basically the pellets in itself were balanced according to these rations. So TDN very high at almost 80 here, group protein at 16%. This is one of them. That's the medium diet. NDF 42, indigestible NDF or INDF very low at 6.3, potentially fermentable fiber at 35% here, and then non-fiber non-structural carbohydrate at 33%, and then obviously also balanced for calcium to phosphorus ratio of 2.17, and yeah, completely balanced and very, very healthy and conducive for high lactation for ewes, right? And this feed formulation tool can be found on the sheep program website. And obviously it can also be used to balance rations that do not consist of fully pelleted feed. All right, so let's take a closer look here. These 3 diets, low soy hull, medium soy hull, and high soy hull, contained in the percentage of the dry matter 35, 42, and 50% soy hulls, right? So the soy hull content went up in those diets, and at the same time, the cornmeal went down, all right? So basically this was counterbalanced. As soy hulls went up, cornmeal went down. So basically structural carbohydrate, NDF, fiber, increased, while non-structural carbohydrate, starch, and sugars decreased. And then wheat mitts were in there to as a pellet binder, basically soybean meal to balance for protein, some molasses to keep it from dusting, calcium carbonate, Cornell sheep premix, and ammonium chloride. So that was in there to prevent urinary calculi in our rams, because we did feed that pellet to lambs as well, right? And pellet binders. So those are the 3 diets. Now looking at the chemical composition of these 3 diets, right? Or the feed components as they came back from dairy 1. So all of that was analyzed by dairy 1. I want to point out the NDF, the fiber, and the non-structural carbohydrates, and then some calculated values, right? So we have our low soy hull, medium soy hull, and high soy hull diets. So the NDF here is the lowest, right? And it goes up. And at the same time, non-structural carbohydrate here is the highest and goes down, right? And those were significantly different, these 3 diets. So now looking at the TDN, or the total digestible nutrients, here, definitely a linear relationship, right? It goes down as the content of corn goes down, or as the fiber increases. And the same is actually true for the mcals per kilogram of net energy available for net energy available for lactation in mcals per kilogram. It also goes down, unsurprisingly, as the corn goes down, right? So now, what does that mean? What would we expect, right? And so definitely take away the higher proportion of corn offers a higher TDN, a higher energy, right? So more propionic acid as glucose precursor is available. How does that influence feed intake is a question. And how does that influence nutrient availability and subsequent milk production, right? Like, does it hold up? Like, does more TDN and more NEL mean that we'll have more production or more nutrient availability? And yeah, so first off, looking at the feed intake, it doesn't, right? So feed intake actually here, the total diet in kilogram, we went from 2.11 kilograms to 2.28, and then no difference as the fermentable fiber or the PF-NDF further increases, right? So having more potentially fermentable or available fiber in the diet did not lead to a additional increase in feed intake. Okay, so more NDF does not automatically mean a higher or even a lower intake, right? So that the NDF here that the animals consumed on a daily level had no influence in their intake, right? The intakes were not significantly different. Neither did the non-structural carbohydrate fraction, right? So that went down actually here. So the intake of that went down, right? That also did not have an impact on the total intake, and TDN or NEL did not either, right? And it's interesting to see here that even though just looking at the diet chemical composition, at the component chemical composition, we saw that TDN and NEL was higher here for the low soy hull diet, right, with more corn. But due to the slightly elevated intake of the medium soy hull diet, we actually see a quadratic distribution here. We have more intake of TDN and more intake of NEL per day for the medium soy hull diet compared with the other two, right? So the ewes on this medium diet had the most TDN available to them and the most NEL. And graphically, looking at the intake, again, no difference between the three groups, low in blue, medium in gray, and high in red. However, looking at feed efficiency, or better, the kilogram milk output per kilogram dry matter intake, the medium soy hull diet here clearly was the winner, right? So this actually generated up to 0.3 kilograms more milk per day, right? So feed efficiency for these ewes was the highest. But very clearly, intake has an influence, right? So this slightly elevated intake led to a higher intake of total digestible nutrients and NEL, even though in the feed component data analyses, that was not the case. That was where the low soy hull diet actually had the better, tested better, right? Okay, so now what can we do with this? Let's look briefly at requirements and examples, right, on farm that are maybe more translatable to on farm, because I'm pretty sure that actually not many farms in actual farm setting would feed like that, would feed ad lib pellets and only offer about, I think, 300 grams of hay per head per day on average, right? So suggested feed component levels for use, that's data from Tatiana, or a summary from Tatiana. This all depends on the number of lambs, right? Obviously not early pregnant, because that's when we don't know that, but late pregnant, is there singles, twins, or triplets? Early lactations, do we have singles, twins, or triplets, or late lactation? Same thing, so the number of lambs. And based on that, we can formulate, or we can summarize TDN suggestions, true protein suggestions, and then also potentially fermentable fiber suggestions, right? And we can maybe look here at early lactation with triplets. Maybe that would be the most interesting. So we have a TDN requirement of about 75%. Crude protein should be at 16%, and potentially fermentable fiber, or NDF, should be at 35%. And now looking at some hays, this is also hay data that Todd kindly shared with me. There is quite the selection of hays, alfalfa and grass, right? And we have here our dry matter in percentage, NDF fraction, our TDN, or digestible dry matter, our metabolic fecal losses that are all for forages, about 15% of the dry matter, indigestible NDF, potentially fermentable NDF. Okay, so this is, again, that column is what really is available to the animal, and our crude protein. And so maybe first, let's look at this one right here. So we have a second cut alfalfa, right? And basically, this goes back to that energy table that I showed you earlier. The lignin content is so high, and with that, the potentially fermentable NDF, or the NDF that is available to the animal, is really, really low, right? Only runs at 21% here, so that is very low, and actually too low for, definitely too low for a early lactation ewe, even though the protein content of that alfalfa would be perfect, right? So that would be exactly to requirements. However, we wouldn't, I mean, you can kind of see that in the amount of NDF that's in that alfalfa, right? But if we look at, for example, this one right here, 53% NDF is not, it's different. Oh, actually 42. No, it is really different. Yeah, okay. Yeah, but overall, just saying, you know, merely looking at NDF is not sufficient. Having this value of available NDF to the animal is really valuable. All right, and then maybe here, this is the first cut cannery reed hay, and this has a really high INDF portion, right? So the potentially fermentable NDF is actually really high as well, right? So just by looking at that, you'd say, wow, okay, this is a lot and may even be adequate for a hay. However, this is also really, really high, and at the same time, protein is low. So what does that tell us really is that that must have been a very, very late first cut, right? Because the plant is over mature or old, runs low in protein, which it inherently does, but very low in protein and has a high amount of lignified material or indigestible fiber here. And then maybe the other one worth pointing out is this alfalfa third cut baleage, right? That runs at 26.4% protein, which is very, very high. I'm sure that Tat will talk about that next week as well, and why that does not work really in any setting, and especially not in a dairy setting, because it will have influence on milk quality, right? So looking at the potentially fermentable fiber, again, that's a good value. That's not a good value, right? That is like very, very low, and NDF here is also very low. Okay, so now I guess the last thing before we go into more of like discussion and questions is to just an example of balancing on farm for a meat sheep operation or a meat goat operation. In this case, it's sheep actually without a feed program, and how that could be approached with really like crude back of the envelope math to just check if the amount of concentrate that is being fed is accurate or sufficient, and what the amount of concentrate that we're feeding or deciding to feed, what kind of influence that has on the total value of the ration. So here in this example, we have 150 Katahdin ewes. They weigh 150 pounds, are in their third trimester, and they have 2 round bale feeders available to them. So 1 round bale feeder feeds about 80 ewes, right? When they get towards the end of the third trimester, they may need a third one, but at this point, we're assuming that this is still okay. And in a regular barn shed setting, and they're being fed good quality second cut grass hay, and they're being fed a bale per day, right? So, and likely, 1 bale is replenished every day, so that there's constantly feed available in both round bale feeders. So we have the way to calculate our dry matter intake would that we know our bales are 850 pounds. They run at 90.6% dry matter according to Dairy 1, means that there is 770.1 pound of dry matter available per bale, right? So if approximately 1 bale per day, or if 1 bale per day is fed, and it's a good quality second cut grass hay, there won't be more than 10% waste, right? So this hay will not go through the barn as bedding as well, right? It will be eaten, but 10% waste is fair. So we have 693 pounds of dry matter that is being fed to our 150 sheep per day, right? Based on that, we know that each ewe consumes about 4.6 pounds of dry matter per day, which is about 3.1% of their body weight. Now, thinking that they're third trimester ewes, right, and the uterus grows and restricts the space for the rumen, that I would think is a very realistic assumption to make 3% of body weight, right? So now the question is, looking at our feed values right here, we'll go over that. How do we supplement, right, for early lactation, assuming that the ewe will have triplets and will consume about 8 pounds of dry matter in early lactation, which is about 5.1% of her body weight, right? Like, what will we supplement her hay with, assuming that we're going to be feeding the same exact hay throughout lactation? So here are our feed components. 3 of them, crude protein, NDF, non-structural carbohydrates, in our second cut grass hay. So we run at 11.9% crude protein. So we're protein limited here. That is first limiting. That is what we need to supplement. We have 58 NDF, that's a good value. Non-structural carbohydrate at 21 is also great. Based on our component evaluation from dairy 1, right, our feed chemistry, we can calculate certain indicator values. TDN will be calculated by dairy 1, or any feed lab runs here at 60. And then we have our metabolic fecal losses at 15, our indigestible NDF at 25, and our potentially fermentable fiber at 33. So those are our calculated indication values. And we have a caloric content of 1.01 ME and mCals per pound. All right, so now going back to the previous slide, early lactation, triplets, right? We want 16% of protein, right here. This is what we want. We do not have that, right? We have 12%. So again, first limiting here is the crude protein. So our supplement choice is something that contains a higher crude protein value. And because of that, because we are looking for a crude protein supplement, we can go for a lower NDF or a non-structural carbohydrate concentrate, like a lower carbohydrate focused concentrate, a lower energy providing concentrate. So I picked here, just to try it out, the Cornell pellet that I showed you earlier, and we have 17% crude protein, NDF 31.9, non-structural carbohydrate run at 41.1, right? So that is fairly corn heavy. It's the 40 diet. And so what we can do is we can just apply Pearson's square here. I'm pretty sure you all are familiar with that. I'm just going to go over that. So the supplement crude protein is 17. The forage crude protein is 11.9. We have a desired value of crude protein of 16, right? So we're going to subtract diagonally. So we're going to do 17 minus 16 equals 1. We're going to do 11.9 minus 16 equals 4.1 if we ignore the minus sign, ignoring the minus, right? And then 4.1 plus 1, this gets summed up, 5.1. And we have 5.1 total parts, right? And then the last piece of the mass is 4.1 divided by 5.1. So 4.1 parts divided by the total parts, and 1 part divided by the total parts. So we land at 80% forage diagonally, right? And 20% supplement, right? And if we go back to our 8 pound assumed dry matter intake here, we land at 6.4 pounds of forage intake per day per ewe, and 1.2 pound requirement of supplement. So 1.2 pound Cornell pellet requirement per ewe per day, right? So now, and if we take that a little bit further, our ration now, right, looks like this. We have our desired 16% of protein. We have 52.7% NDF, 25% non-structural carbohydrate, and our calculated indicator values look also different. We have about 63 TDN. Our metabolic fecal losses look different, right? And so does our potentially fermentable fiber, all right? So now, going back to our requirements, we could say, oh, TDN is low, right? Triplets and early lactation should be at 75. However, looking at the metabolizable energy available, which is spot on, looking at the protein that's spot on, and the NDF that is also good, I'd be inclined to let that go and say that really feeding 1.2 pounds of that concentrate would be a good idea. Yeah, and that basically is a very crude math, back of the envelope example if you're not using a feed program. And yeah, I'm gonna stop at this point and X out of that. Dana is asking, is it safe to assume that the ideals apply across breeds? Yes, I would say so. I mean, Tatiana, maybe you have a different insight here, or Rich, maybe you, but I mean, what it really depends on is the amount of, or the litter size, right? Like how many lambs does the animal have? Yep. Okay, and I'm happy for any questions, comments, or discussion. And I'm really hoping you cannot hear our dog in the background. It was constantly whining. If so, I apologize.
I think one thing I'd point out is part of this gives us the example of why when you feed alfalfa hay to your dairy goats, which so many of us do, they're going to be leaving a lot of the stems, generally. And that's because they're able to be selective eaters, and they're able to say, I'm not going to eat the stems, I'm going to eat the leaves, pretty much only the leaves. And so because of that, that I think Rich Toby in the past has talked about how when you sample a feed, you want to sample what the animals are actually eating. And so I think with alfalfa, that's one of the big things you often need to do is sample what the animals are actually eating. Versus a second cut grass hay, you often don't see a lot of, it's often very uniform if it's a good quality orchard grass or something. And so often there, the animals aren't doing a lot of selection through it. But with alfalfa, we often see a great deal of selection. Or like on canary reed, you would also see selection, but canary reed tends to be so lignified so quickly that they can't do that. So Carly's asking, I've started feeding soy hull pellets in addition to our ration. This was interesting. Is Tatiana going to talk more about the role of fermentable fiber next month? I actually am, and I'm going to more just show some specific case studies, and what we might often think is the quick solution and why that quick solution might not work well, in fact. But yeah, I'll talk more about fermentable fiber and probably also a little bit about bypass protein next time. So are there more questions right now? I know that for me, Niko, I get really confused about what the role of propionic acid is, and of the role, of all those volatile fatty acids, and which ones contribute to fat production in milk and which ones contribute to the milk directly. So it was really nice to have you do this review or to go through this, but I'm going to go back and do some reading up now. I know that NDF neutral detergent, so baby shampoo, breaks down your lignin and your cellulose, and then your more digestible or more fermentable hemicellulose. And the problem is that it would just be perfect is if acid detergent fiber digested, only broke down lignin, but instead it breaks down lignin and cellulose and not hemicellulose. And you go, well, we don't really need the division between cellulose and hemicellulose. We need that division with lignin. But so when you do more a lignin analysis like Dairy One does, is that more done? Like I'll see sometimes figures like 30 hours, 40 hours, 50 hours when they're doing lignin, and what does that refer to?
That basically refers to the rate of digestion, right? So how quickly is a carbohydrate digested or a feed digested, right? So sometimes it takes up to 100 something hours for a certain fiber molecule to be broken down by the microbes.
So
And
that would be related to the rate of passage that you were talking about earlier?
also, yes, exactly. But first off, the rate of digestion. So how fast is digestion? And the faster digestion is, the higher passage rate can be, right? Because the rumen gets emptied out more frequently. Yep.
Oh. So why don't we go ahead and cut off the recording now? And then we can go on to discuss some other stuff if people want to.